Let's start today's class. So we were talking about indices, surds, and logarithms. So yesterday we did some examples about indices and solving exponential equations. Okay, today we will continue from where we stopped. So we will do two more examples about exponential equations, and after that we'll talk about surds. Okay, then in the next session, second session, we will study logarithms. So here, where we stopped yesterday, we did like 5 examples. This is another example involving indices or exponents. So it's here it says that given that y equals this is a kind of function, right? It may describe a kind of phenomenon. Okay, and it says that y equals 7 when x equals 2 and y equals 22 when x equals 3. Find the value of a and of b. So while we are practicing these questions, when we actually face any problem involving indices or exponential equations, so by practicing this, number one, you gain some self-confidence. Number two is you feel very comfortable to deal with problems involving exponential equation. If you are a business student, especially, you will see this kind of stuff. Number one, when you are dealing with future value problems or compound interest problems or continuous interest problems. And also when I talk about some kind of growth, okay, growth of population, okay. So here we are given this function. This is how this equation describes how y and x are connected to each other, right? So here, step 1, y is equal to a times x to the power b minus 5. So first, the question is, this is a function, right? We need to determine the values of a and b. So using this given information here, the first one and the second one. So the two pieces of information is given, and here we have two variables, unknowns, right? By using this, we can determine the values of a and b. So it says that when y equals 7, x equals 2. So y equals 7, here we have a times what is x? X equals 2. 2 to the power b minus 5. And if I substitute the second thing here, y equals 22 when x equals 3, right? If we substitute here we have y equals 22 equals a times, what is x? X equals 3. 3 to the power b. Here we have negative 5. Now here we have system of equations, but they are not linear equations, right? It's not like ax plus by equals c, right? Because here we have exponents. That's why this is exponential equation. So here, if you simplify this, what we get here? Take 5 to the left-hand side. So here we have a times 2 to the power b equals 7 plus 5. That's equal to 12, right? The second equation, take this 5 to the left-hand side or add 5 to both sides of the equation. 22 plus 5 is 27. So here we have a times 3 to the power b is equal to 27. Here we have two equations and two variables or two unknowns. How can we find this? By doing either substitution or elimination, right? So here if I just divide the second equation by the first one or first equation by the second one, what happens here? Here we have a times 2 to the power b is divided by a times 3 to the power b, which is equal to this thing equals 12 here over this thing equals 27. Right? So as you see here, this a's, they cancel out each other, right? 2 to the power b, 3 to the power b, and they have a common exponent so that I can write it under one exponent. So we can write it as 2 over 3 to the power, here we have b, equals, how about here? First, you can simplify this. Here we have 12 over 27 is equal to 3 times 4 and 3 times 9, right? These 3's, they cancel each other. 4 over 9. What is 4? 2 squared. 9 is 3 squared. So that's equal to 2 over 3 squared. So here we have 2 over 3 squared, right? So now here we have 8 to the power b, and here we have 8 to the power something, right? So these bases are equal, and also for these things to be equal to each other, the exponents must be equal to each other. So from here then, b is equal to 2, right? Now, if I substitute this value into either the first or the second equation, we can determine the value of a. So that is the first step, right? And here we have the second step. And the third step is substitute here, for example, a times 2 to the power. What is b? It is 2. That's equal to 12. And from here, what is a? A equals, here we have 4. 12 is divided by 4. That's equal to 3. So dots, 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 and here we have the value of a is 3, and value of b is equal to 2. Okay. Continue. Another example. Solve the simultaneous equations. Yeah, simultaneous equations, but they are not linear equations. They are exponential equations, right? So here, the first equation is 3 to the power x times 9 to the power 2y is equal to 27. And the second equation is 2 to the power x times 4 to the power negative y is equal to 1 over 8. Okay. So as here, this base is actually this 9. I can write it as a power of 3. This 4 I can write as a power of 3. And also here we have 27, which can be written as a power of 3, and also 1 over 8, right? We can write it as a power of 2. So here we have 3 to the power x plus, here we have 3 to the power 4y, right? Here we have 3 to the power x times 3 squared to the power 2y. On the right hand side, 3 cubed. How about here, 2 to the power x times 2 to the power 2 or 2 squared to the power negative y equals, how about here, we have 2 to the power negative 3. So here we have 2 times 2y, that is 4, x plus 4y, right? Here we have 4y equals, on the right hand side, we have 3 cubed. And how about the second equation? From the second equation, here we have 2 to the power x, 2 times negative y, it is minus 2y, and if you just add them up, because they are multiplied, minus 2y. That's equal to 2 to the power negative 3, right? As you see here on both sides, actually the bases are equal, right? Here we have 3, here we have 3, here we have 2, here we have 2. So for these equations to be actually true, right, the exponents must be equal to each other. So from the first equation, we have x plus 4y is equal to 3, right? From the second equation, x minus 2y is equal to negative 3. What do we got here? We have just converted this exponential equations or a system of exponential equations into linear equations, right? Simultaneous linear equations. Both are linear and we know how to solve them, right? So if I just subtract the second equation from the first one, x minus x, that's equal to 0. 4 minus minus 2, it is 6y, right? 3 minus minus 3, that's equal to 6. From here, y is equal to 1, right? Now, if I substitute here, x plus 4 times 1 equals 3. What is x? X equals negative 1. So the answer is x equals negative 1 and y is equal to 1. Okay, that is the solution of the given exponential equations. All right, that's all about exponential equations. Let's talk about surds. So we know that a rational number is one that can be expressed as m over n, right? Where n are integers and n is not equal to 0. Because if n equals 0, we do not have this 0 division operation. We cannot divide any real number by 0, right? That's why here we are excluding that n is not equal to 0. So if we just write any number in this form, or if any number is in this form, then we say that it is a rational number. Right? For rational number, for example, any fraction actually, it's a rational number, right? What are these? We're talking about this rational number 1 over 2, 3 over 4, 1 over 10, 10 over 2, dot, dot, dot. These are all rational numbers. If we can write any number as a ratio of two numbers, right? Like in the fraction 10 over 2, 2 over 1, 1 over 3, 3 over 6, these are all rational numbers. But in real number system, also there are some numbers, they cannot be written as the ratio of two integers. Right? What are these numbers? For example, square root of 2. This if we are given this number, square root of 2, we cannot find any two integers where that is equal to a over b. Is it possible or not? It's never possible. We cannot show any number. When you divide integer by another integer, it gives us square root of 2. So if a number or real number cannot be written in this form, then we say that that is a rational number. Okay. Is it used? Of course. For example, one simple example where it is used. Let's say you have a field in square shape. Okay. So all sides are equal and all interior angles are 90 degrees. That means it's a square. Okay. You can just assume that maybe if you're living in ideal world, okay, here, this is your house, all right, here, your auntie's house, let's say, all right, and you want to make an interconnection between A and B, okay, and the length of this side is, let's say, 1 kilometer, and that's also 1 kilometer, 1 kilometer, 1 kilometer. Now, if you ask a question, so if we want to buy a kind of cable that connects A to B. All right. Then exactly what must be the length of this cable? What must be the length of this cable that connects A to B? So we are talking about this thing. Okay. So if you find this AB by using Pythagoras theorem, what we have here, this AB is equal to square root of A squared plus B squared, right? A squared plus B squared equals C squared. This is right angle triangle. So here we have 1 squared plus 1 squared, which is equal to square root of 2. So the length of this cable must be exactly square root of 2. Okay, but in real life, you can just estimate this as square root of 2 is about 1.42. So if you buy 1.5 meters, that would be enough. Or 1.5 kilometers, that would be enough. All right, but to be exact, this cable, the length of this cable must be square root of 2. How actually these irrational numbers are used? In application, there are a lot of in many applications, these irrational numbers are used. Okay, but here, anyway, what you have to know here is, so here we have two different numbers. Number one is, here we are talking about rational numbers that we denoted with Q, and we have some numbers, they are not rational numbers. That we just denoted with Q cap, all right? So these numbers together form real numbers. Rational numbers, union irrational numbers, they form real number, okay? If you just pick any number on the number line, it's either rational number or irrational number. Okay, if you pick any number on the number line, this is our number line. Let's say here we have 0. If you just pick any number, it's either rational number or irrational number. If it is 3, for example, it is rational number. Here, if you pick, for example, square root of 3, it is a rational number. If you pick here negative square root of 2, it is a rational number. If you pick here, for example, negative 4, that is a rational number. Okay, so rational number and irrational number together, they form, what is it? Real number. Anyway, usually most of the numbers involving square roots or cube roots, like square root of 2, third root of 5, square root of 7, square root of, let's say, 11, square root of 20. These numbers are irrational numbers, and they are called surds. Okay, that's involving this root, we call them surd. So in order to simplify these surds, we're going to use these two rules. Okay. Number one is square root of a times square root of b. That's equal to square root of a times b. Why is this so? Because we know that by the definition, the square root of a, we define this as a to the power 1 over 2. How about this one? It is b to the power 1 over 2, right? And exponents are the same. I can write it as a times b to the power 1 over 2. Again, using the definition, I can write it as square root of a times b, right? But here there should be positive because under the square root, we cannot write negative number. If it is negative number, it wouldn't be real number, okay? In a similar way, but only here we have one exception. B should be greater than 0, right? Because we cannot divide any number by 0. All right, the surds such as 3 plus square root of 5 and 3 minus square root of 5, we call them conjugate surds. All right, why? Because if we multiply them together, the result will be a rational number. Right? For example, if we try here, 3 plus square root of 5 and times 3 minus square root of 5, which is equal to, okay, which is equal to a plus b, a minus b, right? So here we have 3 squared minus square root of 5 squared. Here we have 9 minus 5, which is equal to 4. Okay, so that is what is 4. It is rational number. How about this thing? It is a rational number, surds. This is another third, right? So this surds, actually, when we multiply them together, if they are conjugates of each other, so the result is always rational number. Okay, that is one important thing in math. A lot of times, especially if surds appear in the denominator of fractions, we may want to, how to say, rationalize the denominator. At the time, we need to apply this operation of this rule so that we can change its denominator into rational number. So the general form of conjugate surds are a times square root of m plus b times square root of n and a times square root of m minus b times square root of n. Actually, if the powers are different here, if we have like 3, 4, 5, depending on this, we can produce some other thing. But here we are talking about square root of something. Okay, so these are conjugates. So if you multiply them together, here we have something plus something. Let's say x plus y, and here we have x minus y, right? And using the formula that is equal to x squared minus y squared. What is the square of this term? It is a squared times m. A squared minus m. And here we have b squared times n. But here we have minus. We have two examples about surds. Simplify the following without using a calculator. Okay. So A, how do you simplify this? The first one, this 50, I can write it as square root of 25 times 2, right? Plus, how about this 72? We can write it as 36 times 2 plus, and here we have, I can write it under a single square root, 160 over 5, which is equal to, here we have 5 squared, right? I can take this out, that's equal to 5 square root of 2, because square root of 5 squared is equal to 5, and plus, how about here? Square root of 36, that is 6 square root of 2, plus, and 160 is divided by 5, that's equal to 32. 32 is 16 times 2, which is equal to, here we have 5, here we have 6. If you just take this out, that will be square root of 16, that's equal to 4, right? 5 plus 6, 11, 11 plus 4 is 15. And here we have square root of 2. So we have simplified the given surds. B, how about here? Actually, it's not, they are not conjugates of each other, right? Here we do not have a plus b, a minus b. So you should not get confused here. So what we are going to do here is just expand this, right? Here we have a plus b times c minus d, which is equal to, first I need to multiply this by this, 2 times 3. It is 6, and square root of 3 times square root of 3, that is 3. Done. Here we have minus because of this, 2 times 4. It is 8 times square root of 3 times square root of 2, that is square root of 6. Okay. Plus, now I should multiply this by this, right? 3 times 1, it is 3 times square root of 2 times square root of 3, that is square root of 6. And here we have minus 1 times 4, it is 4, right? Square root of 2 times square root of 2, that's equal to times 2. Equals 6 times 3, 18, minus 4 times 2, it is 8, minus 8 plus 3 minus 5, square root of 6. Or that's equal to 10 minus 5 square root of 6. Simplify, right? We cannot simplify this any further. Another example, rationalize the denominators of each of the following. So here, as you see here, we are given fractions here, right? And denominators of these fractions are irrational numbers or surds. Okay. So we need to rationalize their denominator. The first one to do this, we should just multiply the denominator by its conjugate. So here the first one here we have 6 over square root of 3, right? Is this conjugate, the square root of 3 is square root of 3. So I will multiply the numerator by square root of 3 and denominator by square root of 3, which is equal to square root of 3 times square root of 3, that's equal to 3. And 6 is divided by 3, right? 6 is divided by 3, that is 2 square root of 3. Okay. How about question B? Also, we need to rationalize the denominator here. So first, we need to multiply. As you see here, we need to recognize it is just a irrational number. It's called 3 plus 1. And we need to multiply numerator and denominator by the conjugate of the denominator, right? So here we have 4 over square root of 3 plus 1. And conjugate of this expression is, so this number is square root of 3 plus minus 1. So also I need to multiply the numerator by square root of 3 minus 1. Okay. So here we have 4 square root of 3 minus 1. As you see here, a plus b, a minus b. Square root of 3 squared, that is 3. And minus 1 squared, it is 1, right? And 4 is divided by 2. Here we have 2 times square root of 3 minus 1. Okay. The last example, C. Here we have 4 square root of 3 plus square root of 2, right? Over, here we have 3 square root of 3 minus 2 square root of 2, right? So to rationalize its denominator, we need to multiply the denominator by numerator by the conjugate of the denominator. So the same thing but with plus, right? So here we have 3 square root of 3 plus 2 square root of 2. So I should multiply also numerator by the same number. So 3 times square root of 3 plus 2 square root of 2. Because we know that if you multiply the numerator and denominator of the fraction by the same number, the value does not change. Or by the same expression, anything non-zero number, right? It does not change the value of the fraction. So we multiply by the conjugate of the denominator. Equals, let me draw a bit longer line here. So let's start with the denominator. 3a minus b, right? A minus b, a plus b. So the square of this number is 9 times 3, that is 27. Minus 2 squared, 4. And here we have 2, that's equal to 8. Done. How about the numerator? Multiply this by this. 4 times 3, it is 12 times square root of 3 times square root of 3, that is 3. Okay. Plus, multiply this by this. 4 times 2, it is 8 times square root of 3 times square root of 2, that is square root of 6. Plus, square root of 2 times 3 times square root of 3, that is 3, right? square root of 6. And the plus 2 times square root of 2 times square root of 2, that is 2 times 2 equals, so if you simplify the numerator, 36 plus 4, that is 14, plus 8 plus 3, 11, square root of 6, over 27 minus 8, it is 19. So we have rationalized the denominator of the given fraction. Okay. So that's all for Surds and indices. Okay. And there are a lot of questions in the paper I share with you. So you're going to practice those questions. All right. If you have any question anytime, we can have a discussion. I will finish this session with this quote. It is Mark Twain. The secret of getting ahead is getting started. The secret of getting started is breaking your complex, overwhelming tasks into small, manageable tasks, and then starting on the first one. Okay. And how is it related to our math course? For example, let's say we are doing chapter 10 now. All right, we'll just have a look. There are a lot of questions, and you may just worry, how can I finish all these questions in 1 week or 10 days? Okay, and without putting this all these worries aside, okay, so the first question. Okay, exercise 10A, the first question started. And as you do more and more, you get more motivation, you get more inspiration, and even the hard things become easy things. Because once you get actually enjoying solving problems, that the big burden on your shoulder becomes, I would say, the kind of force that is pushing you forward. All right, that's what I understand from this quote. Guys, now let's have a break, okay? After 10 minutes, we will continue. Thank you very much. See you after 10 minutes.